Welcome to lecture number 17 for ECE 376 Embedded Systems, D2A Converters. Now previously we looked at A to D converters. That takes the real world and converts it to a binary signal so the PIC processor can read it. That's for sensors. There's also D2A converters that lets you take the PIC, have it output a binary number, and what comes out is an analog voltage. So you don't have to have things just being 0 volts, 5 volts, off and on. You can have shades of gray. You can go 0 to 5 volts, in this case with 4095 different levels. What that lets you do is you can now output a sine wave to drive a speaker, so you get a nice clean whistle rather than a sharp noise. You can output other periodic waveforms, like build a cello, violin, tuba, output a triangle wave, sawtooth wave, other waveforms like that. You can control the speed of a DC motor. You can control the brightness of an LED. You can also control the speed of an AC motor, just name a few things you can do. To start with, the PIC has a built-in A to D converter. It does not have a D to A, however, so you have to add one. In your kits, there should be an MCP 4921. That is a 12-bit D to A converter. To connect it to the PIC, you need to have power and ground, of course. So pins 1 and 6 go to power, 7 and 5 go to ground. The input pins, CS is chip select, clock is CLK, and this is your data line. Now the way the formatting looks, when you send data to the chip, what I do is I bring chip select low, that's the start of the message. I then send the data, most significant bit first. The first 4 bits are always 0011. That tells the D2A converter to set up for one-time conversion scaled as 1 times the reference. So the output's going to go 0 to 5 volts. And then your 12 data bits. The clock line goes high once for each bit. So to illustrate that, this is a program I'm going to look at in just a sec. This outputs a square wave. I've got my 3 data lines, RC0, RC3, RC5. Going to chip select, clock, and data. The blue line here is your chip select. When it goes low, there's my message, end of message, and that's my clock line. I send 16 clock pulses. If I move this over one, that's my data. I'm sending data to output 2 different voltages, which is what you're seeing there. Now for the software side, I have a subroutine. I'm going to pass it a number, 0 to 4095, and output a voltage. 0 goes to 0 volts, 4095 goes to 5 volts. So the way I do that is I first have to make sure that the 3 output pins are output. I'll then mask variable X, pull off the least significant 12 bits, and replace the high 12-bit or high 4 bits with 0011. So this tells you that your message is going to look like this. It's 0011, then your data. I then start the process. All pins have to start out high. Chip select low, going low is the start of message for each bit. I'll check the most significant bit. If it's a 1, send a 1, otherwise send a 0. Pulse the clock low, then high. And in the same time, I'm going to shift X left, then repeat. I'll take the next bit. If it's a 1, send a 1, otherwise send a 0. Pulse the clock, next bit, next bit, next bit. So what you're left with is this. Chip select goes low, I send my data bits, and let's pull this pin over 1. And there's my clock. And let's see if I stop this so you can see it. Oops, wrong button. Oh, anyway, you saw that. So the D2A converter outputs 0 to 5 volts. Suppose I want to output -10 to +10 volts. What I would need is an amplifier that multiplies by 4. Again, a 5-volt spread goes to a 10-volt spread, or 20-volt spread. So that's times 4. And midband is 2.5 volts here. Midband here is 0 volts. So I'm going to offset it by 2.5. So what this does is create the function y equals 4 times a minus b, or 4 times a minus 2.5. So the output here goes from minus 10 to plus 10 volts. Some things you can do with this. Suppose I want to create a different waveform. And I want the waveform to go between plus 2 volts and minus 2 volts after amplifying it. The voltage at the output of the instrumentation amplifier, this guy right here, Y, is going to go minus 10 to plus 10 volts. The D2A converter actually goes 0 to 5 volts. And the input to the D2A is a number, 0 to 4095. Again, 0 is the minimum, 4095 is the maximum. So what I want to do is figure out the range of voltage that I want to output. If I want to output minus 2 volts, I output 1638. Plus 2 volts should be 2457. So here's a couple waveforms you can generate. For example, let's do a square wave. If I want to output a 100 Hz square wave, I'm going to output 1638, which is minus 2 volts after it being amplified, 2457 plus 2 volts after being amplified, and then put in a weight. This number right here is kind of trial and error. It corresponds to half a millisecond. If I look at the output then, this is what I see. I have a square wave going between the two numbers, and the frequency is about 100 Hz. And a little bit off. That's due to the timing. This number is just a hair off. So I can output a square wave. Other waveforms I can output. If I were to count from 1638 to 2457, I'll get a ramp. That produces a sawtooth wave. So here's what that looks like. Inside the code, where are we? Right here. I'm just going to count. When I get to 2457, I'll reset the count. The output then looks like this. Here I'm counting up. I'm going to go from the minus 2 volts to plus 2 volts. Reset. That's the sawtooth wave. And it's kind of interesting if we look at the data line. Well, here's chip select. Let's go look at data. So there's the data. I'm counting really, really fast. Here's the clock line. And sending out 16 bits of data. And the chip select line. And going back to the output. Slow down the time scale. Really nice oscilloscope. You tap on the screen, and that sets the time scaling, getting it bigger. There we go. Too much. So that's a sawtooth wave. Another waveform. If I were to count up, then count down, then count up, then count down, that's a triangle wave. Sine wave. Well, there's a couple ways to do a sine wave. I could use the built-in function sine in MATLAB. The problem with that is sine takes a lot of clocks. I think it takes over 1,500 clocks to implement sine. That really slows it down. So can I come up with an approximation for a sine wave? Well, one idea is the following. This is a parabolic sine wave. I want to have a sine wave that has a period of 64 counts. So these will be 64 clocks going between here, the start of the sine wave, and the end of it. For the first half, that's a parabola. I'm going to go from 0 at x equals 0 to 0 at x equals 32, which is this function right here. Correction, 128-point sine wave. So 0 and 64 are right here. The peak is at 32. I'm going to scale it so that the peak is the amplitude, or half the peak to peak. offset by the midband voltage 2048. These are actually parabolas. That's a parabolic sine wave. If you're a Mutant Ninja Turtle fan, Season 1, Episode 2, somebody broke into the mad scientist lab and stole a parabolic sine wave generator. This is a parabolic sine wave. So we are now famous in terms of Mutant Ninja Turtles. You understand Season 1, Episode 2. If I output that to the D2A converter, this is what I get. Again, these aren't actually sine waves, that's a parabola. The way you tell it's not a sine wave is you look at the harmonics. A sine wave has no harmonics. This one actually does have a third harmonic. It's small. It's down by a factor of, 3 cubed, 27. But it is there. Another way to do a sine wave is a lookup table. So here in MATLAB, I'm going to generate a sine wave with 16 points. So I just have t going between 1 and 16, scaled, so it goes 0 to 2 pi. My output is going to be a sine wave. I want it to be centered at 2047 plus minus 409, gives me the amplitude, and convert to an integer. So these are the numbers that I want to output to the D2A converter. I'll then put that in a lookup table. So this is the way you set up a table in MATLAB. This is a constant. What the constant means is store this data in program memory, in ROM. If I take that out, store it in RAM, and you actually have more program memory than RAM, either way works. But this is a table with the completely original name called table with 16 elements. These are the voltages I want to output. Then the main routine, what I'm going to do is just spin through the table, count mod 16, output the ith entry of the table, and then wait. This is what I get. I get these stair steps. I output the first number, wait, output the second number, wait, and so on. That's a sine wave. Do this with more points, I can get a smoother sine wave. And this is kind of neat. This is with a UPOOK oscilloscope. I really like this guy. I highly recommend. They're $129 on Amazon. Price is dropping. I switched over to, going on here, I turned on the Fourier transform. So what you see is this. This is the frequency response of a sine wave. It's got the first harmonic, that's your sine wave, plus there's a bunch of higher frequencies up here. This isn't a pure sine wave, you can tell by the squares, these stair steps, but it's pretty darn close. With a little bit of filtering, I can get rid of these high frequency harmonics and get a sine wave. Switching over to a triangle wave, I change the coupling to AC coupling, so it's a bit easier to see. Here's the frequency content. Again, triangle waves also have odd harmonics. They're down by a factor of n squared. Then a square wave, you can see square wave has got the first, third, fifth, seventh, ninth, 11th. Square wave, the harmonics drop off as 1 over n. So really the frequency content, the harmonics, tell you what kind of waveform it is. That leads to other things you can do. Use a different lookup table. I can generate different sounds. This is the frequency or the signal of a violin, trumpet, flute, oboe. So if you ever see an electronic organ, that's all they're doing. They're changing the shape of the waveform. Instead of being a sine wave, output different waveforms, you get different instruments. And you can see that with your cell phone. This is a function called spectroid. If you do the different sounds like whistle, a whistle is a fairly clean sine wave. You can see it's got a strong signal right there. If you do different vowels like ah, that's the frequency content of the letter A. Do a hard A, E, I, O, oo. Each vowel has different frequency content. So you can have artificial speech. just by adding the signals together, and you get the different sounds. If I go over to oscilloscope, let's close this one down. There we go. You can see what the waveforms sound like. So like here's a whistle. Again, whistles are a nice clean sine wave. Letters, ah. Record that, throw that in a lookup table. I can play the sound of an A. An E, E, I, O, oo. Again, by using a lookup table, I can have the D2A converter output these waveforms and get the different sounds. So that's one use you can do with the D2A converter. You can output sine waves, different sounds like that. Another use of a D2A converter, I can do things like control the speed of a motor. Now rather than being binary on-off, I could have analog voltages. That's what this does. The D2A converter outputs 0 to 5 volts. What this is going to do is for an op amp, V plus equals V minus, so this is also 0 to 5 volts. This is a voltage divider. X is 1/4 of the output, so this has to be 4 times X. So as X goes between 0 to 5 volts, the emitter goes between 0 and 20 volts. The 0 to 20 volts goes across the motor. The transistor acts as a current amplifier. So the TIP transistors have a gain of 1000. If I want to output 1 amp to the motor, the op amp has to output 1 milliamp. And op amps aren't real powerful, but they can do 1 milliamp. Times 1000 gives you 1 amp. This converts a cheap op amp that costs, I think, 40 cents into an expensive op amp that costs $18. You can buy op amps that can do 3 amps, but they cost $18. Or if you add in a transistor for 40 cents, I now have an op amp that can do 3 amps. So this circuit will output 0 to 5 or 0 to 20 volts, add up to 3 amps. For a motor, voltage is speed. Now the D2A converter can control the speed of the motor. Another thing, suppose you want to output current. In circuits 1, you had current sources. Well, this is the circuit for current source. This one up here is the circuit for a voltage source. The way this one works is the A to D or D to A converter outputs 0 to 5 volts. That 0 to 5 volts matches up V minus, so this is 0 to 5 volts. This is a voltage controlled current source, also known as a resistor. 5 volts at 50 ohms is 100 milliamps, so this will force anywhere between 0 and 100 milliamps through that resistor. Where the current comes from is your 10 volt supply. So this current is roughly this current. It's a little bit different because beta is 1000, so 1 part comes from the base, 1000 parts comes from here, so this is off by 1 part in 100 and 1001. It's basically the same. So this goes 0 to 100 milliamps. The current through the LED goes 0 to 100 milliamps. So this is a current source. I can specify the current through the LED very precisely with 4095 degrees of gray. And for LED, current is brightness. If I replace the LED with a motor, for motors, current is torque. I'll have a constant torque motor. Eventually, if I apply constant torque, it'll speed up and eventually max out. Max out is I can't get more than 10 volts across the motor. So it will clip. But initially, it'll have a current control device. Current is speed. And what the transistor is doing is the transistor dumps voltage. It dumps whatever voltage it takes to set the current. And it can dump anywhere between 0 and 10 volts. And actually can't quite do 0 because this saturates at 0.9 volts. So it can dump anywhere between 0.9 and 10 volts. But that's a current source. So with this little bit of circuit, I can now take my PIC processor and have a current generator with 4095 degrees or levels of gray. That's one option. Second option, that's actually a little bit better. If I want to drive a DC motor, this is a little bit more expensive. Instead of being 40 cents, this is $40. If you go on eBay and search for advanced motion controls 30A8, you can find these guys. Used, they're about $40. New, they're about $500. This is basically just a big hog and op amp. You feed it power and ground. Power is anything between 20 volts and 80 volts. It's got two inputs, ref plus and ref minus, and you can adjust the gain. If I set ref minus to 2.5 volts, then the difference between the two goes anywhere between minus 2.5 and plus 2.5. I can scale it so minus 2.5 volts gives you minus 30 volts, plus 2.5 volts gives you plus 30 volts. Misspelling 2.5. Anyway, as I go between 0 and 5 volts, I want to go from minus 30 to plus 30. Minus 30 makes the motor spin backwards, full speed. Plus 30 volts makes it spin forward, full speed. And the A30A8T can output up to 20 amps. So this is really just an op amp like the previous one, except it's capable of 30 amps, plus it'll do plus and minus. This circuit right here can only make the motor go forward. If I want to go forward and reverse, use this circuit, and I now have speed control, forward and reverse direction, 4095 different levels of speed, going between minus 30 volts and plus 30 volts. I can also drive three-phase AC brushless motors. The easiest way to do this is, again, go to eBay, where else. You can find these motor controllers for not a lot of money. It's about $13 for a 380 watt DC to AC converter. What this one does is I feed it power and ground, of course. Feed it the voltage that goes to the motor. Here are 12 volts to 36 volts, your pick. Then the VR is your speed. 0 volts is stationary. 5 volts is full speed. And for an AC synchronous motor, frequency is speed. The higher the frequency, the faster the motor spins. Again, what you're doing is you're creating a rotating field on the ABC. The motor will sit there and follow the field. This for an AC synchronous motor. The faster it rotates, the faster the motor spins. So here voltage is speed. There's also direction. If I give it 5 volts, it spins clockwise, or counterclockwise. 0 volts, it spins clockwise. So I've got speed and direction. And with that, I can now drive AC motors. So a little bit of background on motors. Back from physics, if I have a magnetic field and I put a coil, spin the coil around the magnetic field, the voltage induced is proportional to the number of windings times the change in flux, dp dt. As it rotates, the flux going through the area is changing. That produces a sine wave. This is a AC generator. From duality, this is also an AC motor. If I apply this voltage, a sine wave to this guy, it'll spin. So this is a single-phase AC motor. Problem with it is the torque goes to 0 at 0 crossings, so it doesn't have a lot of torque. It's hard to get it started. It actually can spin either clockwise or counterclockwise. That's an AC motor. DC motor, if I can find it, there we are. DC motor has a commutator. What the DC motor does is when I get to that 0 crossing, I switch the leads, and that causes rectification. So this is actually a DC generator, also called a dynamo. From duality, apply constant voltage to the motor, and I'll get the speed. The higher the voltage, the faster it spins. For a two-phase AC motor, if I apply sine versus cosine, I get a rotating field. This is actually a stepper motor. I've got two coils. One goes on the x-axis, one goes on the y-axis. If I apply cosine on the x-axis, sine on the y-axis, I get a rotating field, and the motor follows it. So that's actually how a stepper motor works. I've got cosine on one axis, sine on the other axis. As the field rotates, the motor spins and follows the rotating field. If you make this a sine wave, I get a nice smooth rotation. If I step it, apply x is 1, then y is 1, x is minus 1, y is minus 1, I get a stepper motor. But really, stepper motors are actually two-phase AC synchronous motors. The three-phase motors. If I do the same thing with three phases, I get a rotating field that's a lot smoother. So a three-phase AC synchronous motor is just the same as the two-phase motor. It's got a permanent magnet on the inside, and the magnet rotates as the speed of rotation, or the frequency, is how fast the motor spins. The challenge with this is they have to generate a three-phase AC sine wave to get this to work. Well, that's where these guys come into play. This guy right here is actually a variable frequency drive. The voltage in determines the frequency out. The frequency out determines the speed of the motor. Now, to give you an idea of DC versus AC, which motor to use, DC motors are really nice because they're easy to use. 0 volts is off. In this case, 180 volts is full speed forward. Speed is proportional to voltage. Easy to control. Torque is current. That's what's nice about them. The problem is they're large, inefficient, expensive. This is a motor that's about $2,000 new. You can get them on eBay for $425. Looks like it weighs right around 40 pounds. About the size of a shoebox. That's a DC motor. This is an AC motor. Just came on the market about a month ago. For $93, I have a 3 kilowatt AC motor. 3 kilowatts is about 4 horsepower. So this is right around 5 times bigger than the DC motor. In terms of size, let's see, where's the dimensions? It's a 4-inch by 6-inch motor. Or, for a smaller size, this is about the size of a D-size battery. For $39, you can get a 900 watt motor. This is 2 inches, come back, 2 inches by about 1 1/4 inch, size of a D-size battery. Gives you 900 watts. That's bigger than 1 horsepower. That's what AC motors give you. It's smaller, cheaper, more efficient than a DC motor. But you need 3 phases. It's got 3 wires. If I give this a DC signal, it's going to stare at you, confused, not knowing what to do. I need a 3-phase motor driver to go with it. This one, of course, comes with the motor driver. I feed it the voltage, 0 volts, 36 volts, whatever this one takes. That's your power and ground. The 3 leads go to the motor, and then the signals, we actually will talk about this a little bit later, are 0 volts, 5 volts from the PIC processor, and the pulse width determines the speed. And that's what AC motors do for you. I go from a 40-pound motor that costs $400 used to a motor that weighs 9 ounces, has 1 horsepower. And the question is, what do you do with it? That's the fun thing about being an engineer. I now have toys to play with. The challenge is, what do you do with it? And with the D2A converter, I can now output speeds anywhere between 0 volts and 5 volts, 0 to 4095. And with the driver, control a motor. I can control an LED brightness. I can output sine waves, square waves, sawtooth waves, whatever you want. That's what a D2A converter does for you. Just gives you some options with a PIC processor. That's lecture number 17, D2A Converters for ECE 376.